Hello and welcome to this P2 video tutorial on sequences and series. On the screen as usual is a starter. Pause the video now if you want to give these a go, and then I will go through the answers. Starting with probably the easiest one in the top left. We are adding 13 each time, so this is a 56. Down to the bottom left, a sequence I hope you recognize. The next number is 8, Fibonacci sequence. Across to the bottom right, another sequence of numbers hopefully you recognize as the prime numbers. Going up, we've got 1, 2, 4, 8. That I hope has been enough numbers for us all to get the same answer of 16. In the middle here, I'm going to put the number 31. The reason for that, every other number is 31 here, and then every other number starting with the second one, 29, 30, 31. However, you could alternatively have written a 30 here and claimed this to be the number of days in each month of a leap year. January, February, March, April, May, and therefore June with 30 days. Arguments for both. The final one at the top here, TQ, PH, first letters, triangle, quadrilateral, pentagon, hexagon, and heptagon. If you got all of those, very well done. And we're going to continue on here to the overview. So this first video is a review of arithmetic sequences and series. Now I've put review of here because you should have done a GCSE or something equivalent before coming to the P2 module. So hopefully you've seen arithmetic sequences and series before, so this will be literally a review for you. Then we'll go to geometric sequences and series, which will be very similar, the video styles between the two. And then sum to infinity, use of the sigma notation, recurrence relations, and finally at the end of the module we will solve some problems by modeling with series, which is just putting all of these things to good use to solve word problems. So let's get going with this review. A sequence, to be clear on our definitions, is a string of numbers that follow a set pattern. Now arguably they don't need to be numbers, but in the A-level they always will be. Specifically in this video, an arithmetic sequence has a common difference between consecutive terms in the sequence, and I hope you remember that from your previous work. An arithmetic sequence is also known as an arithmetic progression. Now I won't use that term very often, but you should be aware of it because these two terms, arithmetic sequence and arithmetic progression, can be used interchangeably, and in an exam they could use either one of them. Okay, some examples. Very simple, 7, 10, 13, 16. And using the same notation that you've probably seen before at GCSE, for the common difference D, and for the first term A, I'm going to write on the side here, A is equal to 7 for this one, and the common difference is going up by 3, so that's a positive 3. For the second one, the first term is 6, and it's going down by 7, and I represent that by the negative here, negative 7. So if D is positive, the sequence is going up, and if D is negative, the sequence is going down. The formula for the nth term, which I'm going to call U subscript n of an arithmetic sequence, is given here. I'm not going to explain it because this is something else you should have learned at GCSE or whatever equivalent qualification you did before this. You should be familiar with this. But very quickly again, the letters, A is still the first term in the sequence, D is still the common difference between the terms, and N here and here are the number of terms in the sequence, or the number of the term you're looking for. So for example, the nth term of an arithmetic sequence is given by this formula here. write down the first 5 terms of the sequence. We do this just by substituting in 1, 2, 3, 4, and 5 into n. So the first term, where n is 1, 55 minus 2 is 53. The second term, where n is 2, gives us 51. When n is 3 for the third term, 49. And you can see the minus 2 in the formula here is coming up as the common difference. So I can just continue the pattern. First 5 terms. Find the 99th term in the sequence. Well, in the 99th term we just have n is equal to 99, and we'll put that in, grab my handy calculator. 55 minus 2 times 99 gives me minus 143. And if I write that as, no, let me write that as U99 equals. Find the first term in the sequence that is negative. Now this is a slightly different question. You may have come across this before, you may not. This is asking when the term un, so I'm going to use the formula, when this thing is less than 0. So I'm creating an inequality based on what I know from the term and what the question is asking. So just rearrange that. 55 divided by 2, and we get 27.5. N must be greater than 27.5. But remembering we're talking about the number of terms in a sequence, this n here must be a whole number. I can't have a 0.5 of a term. I can't have term 3.5. It doesn't make any sense. And if we know n must be greater than 27.5, then the first term, where this is true, must be 28. The 27th term will not quite be negative. The 28th term will be negative. Okay, nth term of these arithmetic sequences. Using this formula here, we'll just skip past this formula to create the nth term of these sequences. So let me write that here. Un is equal to a plus n minus 1 d. And just using that, we can go straight ahead. Un is equal to a, in this case 6, plus n minus 1. Now, although I've got 5 terms on the screen, this sequence could arguably continue forever. And I don't know that n is 5 necessarily. I want the nth term, so I'm going to leave n as n times the common difference. The common difference is positive 14. And if you want to, you can expand that out and get 14n minus 8, which might be the way some of you have seen this before. So I'm going to do the next one in a slightly different way. Un, find the common difference, is minus 7. Put that as the coefficient of the n, and then to get 101 with a minus 7 on the first term, I need 108. And that might be the way you've seen it done before, but if you use the formula, you'll get an equivalent expression. First term 101 plus n minus 1 times the common difference, which is minus 7, and if you expand that out, you'll see that they're the same thing. Another example on this, a sequence has a formula, this general sequence, where a and b are constants. Given that we know the third term is 5 and the 8th term is 20, find the values of a and b. We're doing effectively the same thing. We're still using this formula up here, but this time we're going to form some simultaneous equations. So the third term, u3, is a plus 3 minus 1, because we know what n is, in this case it's 3. 3 minus 1 is 2 times the common difference, d. And we know that that third term must equal 5 from the question. We can do the same thing with the 8th term. U8 is a plus 8 minus 1, 7 times d, and that from the question must equal 20. So I've just put n is 8 into this formula here. N is 8, so n minus 1 is 7, a plus 7d, and the answer in the question must be 20. Putting these two together, we can very quickly find that 5d, if I subtract the first equation from the second, 5d is 15. So d must be 3, and following on from that, if d is 3, a must be minus 1. And just as a check, we can try, start with minus 1, common difference of plus 3 gives me 2, 5, 8, 11, 14, 17, 20, 23, and we can check 1, 2, third term is 5, 3, 4, 5, 6, oh dear, 1, 2, 3, 4, 5, 6, 7, 8, the 8th term is 20. Okay, something a little different. We've done the sequences, now to review the series. There's a subtle difference here. The series is where you are adding, summing, some or all of the terms in a sequence. So this first one is a sequence or progression where the terms are listed with commas dividing them. And the second one is a series where you are now adding each of the terms rather than separating them with a comma. They are being summed together. And the sum of the first n terms of a series, again, this is a formula I'm hoping that you've seen before, is this. Now there's two formulas here. This one and this one. And this one here, first term, L is the last term. So the first term plus the last term times by how many terms you've got divided by 2. And the last term is basically the nth term, where n is the number you've got overall. And we know that the nth term from our previous slides, a plus n minus 1 times d. And then if you take this a here and this a here, you end up with the 2a here, and then the n minus 1d is still there. So it's the same formula in a slightly different way, using this last term formula for the nth term. I hope that's something you've seen before. But you might be asked to prove it, so I'm going to go through the proof on the next slide. To do this, you start with the general sequence. Our first term a, and then to get the next term you take your a and you add the common difference, so a plus d. And then to get the next term you start with a plus d and you add the common difference again, so now there's two lots of d's. And then you add it again and again and again, and at the very end our last term here with the formula a plus n minus 1 times d. And you can see here why this is n minus 1, because the first term doesn't have a d, the second one has 1d, the third one has 2d's, and so on. So the last one, the nth term, has n minus 1 lots of d. But to get that formula that we had for the sum, what we're going to do is we're going to turn all of this around and write it again. So I'm just going to write the last term first. So we've got a plus n minus 1 times d. And the second last term, I'm going to write that second. We've got a plus n minus 2 times d plus dot 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 dot. And then the third term, a plus 2d, and the second term, a plus d, and then the first term, a. And the reason we do that is because we can see that when we add this with this, it's the same as here at the end, this and this. And that's what we're going to do. We're going to add these two together. So on the left hand side I'm going to have two lots of this sum, because I've taken the sum and I've added itself. There's two of them now. And that will give me a plus a is 2a. And then I've still got n minus 1d. And then the next one, a plus a is 2a again. And then n minus 2d plus a d is n minus 1d. And you can see that's the same thing. And if I jump to the end, this one plus this one is obviously the same because I've just done that, but the other way around. 2a plus n minus 1d. And of course, this last addition and the first addition are the same. So again, we've got 2a plus n minus 1d. And all of these terms are exactly the same because of the sort of the symmetry. This one has gone over here, and this one has gone over here. So if I add this and this, that must be the same as this and this. And I reduce this by 1d, and I increase this by 1d. So I haven't really changed it. It's the same for each term. And I've got n lots of these. So to do a summation with n lots of these, that's n times 2a plus n minus 1d. And then I've got to remember that I've added 2 of these together, and I didn't want 2, I only wanted 1 of these. So to get rid of that 2, I just divide by 2. And there is our formula. Now, if you've seen that before, it was perhaps quite easy for you. I'm laying it all out because in an exam, if it says prove this, this is what the examiner will be looking for. He wants you to write this and then rewrite it in reverse, add the 2 together to get this, sum these with a multiplication, and then divide by 2 and finish with the formula in the required format. And if you do that, the examiner will be pleased and she'll be able to give you all the marks. You also need to be able to use it. So find the sum of the first 50 natural numbers. We're going to use that formula. Let me just write it up here again. So the sum of the first 50 natural numbers. The natural numbers, I hope the English doesn't trip you up here. 1, 2, 3, 4, and so on. Up to 48, 49, and 50, and we're going to stop there, the first 50. Now here, I'm going to just reverse this just to make it really, really super clear for you. Because if I do what I had on the screen with the algebra previously, it's just a little bit more obvious when you do it with numbers that you get exactly the same thing. So we've got a 51, and 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 a 51. And we've got 50 of these. So what we're going to do, and what the formula does, is 50 times 51, and then we're going to divide that by 2 because that's too many. Let me put that in there as well. So 50 times 51 divided by 2, and we get 1,275. Now this bit here, you would not be expected to do that in the exam. You just go ahead and use the formula. I just wanted to write that out because sometimes the algebra makes it a bit harder to see that these are all going to be the same. Whereas with numbers, it's a bit easier. So for the second example, I'll just going to use the formula. So let's bring it all in. We've got the first term of our series is 32. The common difference is it's going down, so it's a minus 5. Careful with that minus. And the question is find the sum of the first 100 terms. So n, we're going to have 100 terms. And then I just put it in the formula. S of n, I'm summing to the first 100, so I'm going to change that n on there to 100. Just keep good notation here. Is equal to 100 divided by 2 times the first term, 32, plus n, which is 100 minus 1, so that's 99, times minus 5, Put all that in your calculator, see what you get. 2 times 32 plus 99 times minus 5 times by 100 divided by 2 is minus 21,550. Check that makes sense. We start at 32, but you can see it's going down, so very quickly we're going to hit a negative, and all of the ones after that will be negative. So if we add up lots and lots of negative numbers with a few positives, yeah, we're going to get a big negative number. That makes sense. Oh, I've gone over. Okay, find the least number of terms required for the sum of this to exceed 1,000. Now this is one of those sneaky little inequality questions. So we're going to find the sum of this. Well, let me just write that over here. The sum is going to be taken from our formula up on the top left. N divided by 2. We don't know how many n is because we don't know how many terms are required. Times 2 times the first term, which is a 4, plus n minus 1. Again, we don't know what n is yet. That's the question. Times d, the common difference is positive 5. So this is the sum to n. But I don't know what n is yet. What I do know is that I need this thing to be bigger than 1,000. So let me write out the inequality. We've got n over 2. I'm just going to simplify it. 2 times 4 is 8. Plus 5n minus 1. Okay, so that's the same as this thing here. And this needs to be greater than 1,000. So I've got an inequality to solve. Let's go ahead and do it. I'm going to multiply both sides by 2 and expand all the brackets. So I'm going to have 8n plus 5n squared minus 5n must be greater than 2,000. Simplify it all up a little bit. I'm going to have 5n squared plus 3n minus 2,000 must be greater than 0. So I put the 2,000 on the other side to make it clear that this is quadratic that I'm going to be solving. And in an exam you should show your method, but seeing as we're not in an exam, I'm just going to quickly put that on my calculator. Got 5, 3, minus 2,000, 19.7 minus 20. So what I've done is I've solved this equation. And for this equation, n is 19.7 or minus 20.3, both rounded to one decimal place. But this is not what I'm actually asked to solve, this is. So when is this thing greater than 0? There are lots of different methods you can use here, but I'm going to take a little bit of common sense. I can't have a negative number of terms in a sequence. Clearly this is the one. And it's obviously getting bigger, so I'm obviously going to need to be the next number up, not the next number down. So n must be greater than 19.7. Which means that the first term to make this exceed 1,000 is 20. And then if you've got time, use that n equals 20 and this sequence, put it in here and make sure it is above 1,000. Put 19, if you've got lots of time, put 19 in as well and make sure that that's just a little bit below 1,000. And then you're absolutely confident you've got the right answer. Okay, I flew through some of that so fast that it's actually 2 sections in the textbook. And I did that because most of it should have been a review for you. But if you've got the Edexcel International Textbook for P2, you can now practice all of this in exercise 5A and 5B. And maybe I'll see you for the next tutorial on geometric sequences.